And we have two more guys. We have Ed and Vishrut, and they're gonna show us a demo at the end of the presentation. So, okay, before we go to the presentation, let's open up the floor and see if anyone has anything to say to the people around here. Okay, going once, twice, and let's start.
Okay, so thanks a lot for having us here today. So what we are going to do is we are going to talk a little bit about big data, and then we are going to present the product we've been working on for the past couple of years, which is a distributed machine learning platform called Distributed Park. So I'm Jorge Martinez. I'm one of the engineers working on that. I'm working on the platform side, and he's another of the engineers, and he's also working on the platform side. Vishrut is an expert in machine learning. He's working on the algorithms part. So let me get a sense of the audience. Like, how many of you are data scientists? Can you raise your hands? How many are software engineers? Okay, product managers. Okay, so mainly data scientists and software engineers. Okay, so I'm going to start a presentation now. So this is just a little bit of background about me. So I started my career a few years ago in Barcelona, and I was doing like super low level stuff with FPGAs, electronics, and so on. From there I moved a little bit to software, but still low level software, like embedded software, GPUs, and so on. And 2 years ago I moved to the US and I started working on distributed systems and machine learning. And these are the things I'm interested in right now. Okay, probably you've heard this like 1,000 times, right? We live like in the big data era, like there is data all around us. And this data has the potential, right, like to improve our lives, to improve businesses, to improve like the day-to-day lives of everybody. But it's difficult, right, because we have a ton of data, so it's difficult even storing it, so let alone like analyzing it and get some insight from the data. And having all this data, what's happened is like companies used to have like business analysts, like to know, to tell where the business was going. But this was a problem because when you have people taking this decision, they have some biases and so on. And now we have a ton of data, so we can use that data to spot some patterns and to take like better decisions. So a lot of companies are replacing these business analysts by data science and by machine learning. So I'm going to play a quick video around this, like to show the importance that data science has like these days. Hopefully it will work. Okay, wait, let me fix this.
Understanding and innovating with data has the potential to change the way we do almost anything for the better. That's why my administration's opened up massive amounts of government data to the public for the first time, with more than 135,000 data sets available for download at data.gov. Think about the weather and map apps we check every day on our phones, many of which are powered by open government data, along with countless other apps and services. Or our new precision medicine initiative, which joins data science and healthcare to accelerate treatments for disease. We want more Americans to dream up and deploy innovations like these to solve problems, save lives, and create new jobs and opportunities. And that's why I'm so pleased to welcome Dr. DJ Patel as the federal government's first chief data scientist. And that's why I'm asking you to help. As DJ likes to say, data science is a team sport. That's why we want you, America's data scientists, to join us in this effort. Help us build better digital services for the American people. Help us unleash new innovation in areas like healthcare and climate change. Help us change this country and this world for for the better. Thanks.
So this is how important it is. Even the president is talking about data science, right? Okay, so what is a typical workflow like a person would use like to apply some machine learning to get some insight from data? So initially, probably you have your data in a database, or if you are a Hadoop person, maybe you have the data on HDFS. So you take.
Really happy to be introducing our next guest.
Sorry about that. Okay, so you take your data from the database or from it.
Excuse me, your volume's too loud or your microphone's too close to your mouth.
Okay, thank you. So you have your data, it's on a database, it's on HDFS, so you move that data to a machine learning engine to train your models. You train your models using that data, and then you deploy those models back to your database, so you can make predictions of your own data, your old data, or newly arriving data. So this is basically the workflow. Get the data, train some machine learning models, and then make predictions. Okay, and what tools do data scientists use? So according to this survey, R is super popular, followed by SQL and Python. So how many of you, of those data scientists, or everybody use R or know R? Right, so it's a lot of people. So let's talk a little bit about R. And I like this quote a lot. It says, the best thing about R, if it was developed by statisticians. The worst thing is, well, it was developed by a statistician. So what does this mean? Like, statisticians love R because it's super easy to use, like, you can get the stuff done super quick, but it's not like a real, well, how do I put this? It's not like a general programming language like C++, Java, or Python, right? So it's quite slow, doesn't scale well to big data, and it has many issues, like it's not a good language for production, for example. So good thing about it is open source, so you have it's flexible, you can extend it, you have tons of packages with every functionality you can imagine. And the bad thing is what I mentioned, right? It doesn't scale. For big data, you don't have many parallel algorithms. So basically, when you are working with big data, you need tools that work well at scale, right? And we all know, maybe 10 years ago, microprocessors stopped scaling, the clock race just stopped, and chip manufacturers, they just went into multiple cores, right? But when you have a problem big enough, a single machine is not enough. So what people do is they build these clusters of commodity machines, and they write software to take advantage of those machines. So basically, the way to compute big data in a cost-effective manner is scaling up. And another interesting thing about big data is since it's that big, so it doesn't make sense to move data around or to shuffle a lot of data because it's slow. So probably you want to move the code to the data and do computation in place. And this is, for example, the main idea behind the first big data paradigm that was MapReduce. So basically, the data stays in a place and you send code to make computation on each piece of data. So for this, for example, R is a good language because it's functional. That means you can send your functions around to the data more easily. So to recap, so we live in the big data era, right? We have tons of data. We can get interesting insights and patterns from this data. But we need to write tools. We need the right tools, right? Tools that work well at scale, and we should send the code to the data. That is a good paradigm in big data. And following these principles, this is why I designed distributed R, which is a new enterprise class predictive analytics platform, and it's basically extending R to make it work with big data. So distributed R is implemented as an R package, and it's completely open source. It's up on GitHub. The main use case is to be able to analyze data that's too large for regular R. Probably if you work with big data, you realize if you try to process it with R, maybe you get out of memory errors, or it's just so slow, it takes forever to finish. So this is what we are trying to solve. So for that, So we leverage like multiple nodes to work on data in parallel, and as a result, we get like much better performance. But to achieve this, we are not inventing like a new framework. So we try very hard like to use this only as a package and to keep the same algorithms and interfaces that our scientists are use like usually. Okay, so let me tell you how distributed R works. What is the sorry about I don't know why this is flaky. So in distributed R, we have like two elements. So the first one is the master. The master is in charge of scheduling the tasks across the cluster and to send the commands to the workers. So it's basically the guy in charge of scheduling the whole operation. And then we have the workers, which are the ones that do the actual work, that they train the models and they crunch the numbers. So basically they get commands from the master and they do the actual work. Also they own the data, meaning that the data resides on the workers and we don't move it. So the master just sends commands, and we perform the computations on the workers. And the good thing is like they can work on independent partitions of the data in parallel. To make all this work, we have like two main concepts. Like the first one is distributed data structures. So distributed data structures is a way of splitting your data set. So let's say, for example, you have like a huge table with 10 billion rows. So for example, you can say like 2.5 billion rows. Let's say you have a cluster with 4 workers. So you can say like 2.5 billion rows to each worker. Okay. So the arrays, only if you know R, is like an array. So it only works for numerical data. So we also have like distributed data frames and distributed lists to work with other types of data. And the next construct we have is for each. So for each allows you to execute code across the cluster in parallel. So you can run like functions and code on those partitions in parallel across the cluster. Okay, and since this may seem like a little bit abstract, like the data structures and the for each and so on, I'm going to do like a quick demo to show how this works.
So distributed part is open source, right?
Yeah, it's on GitHub.
So what's the HP take on it?
So the question is, distributed R is open source, what's HP's take on it? So, it's open source, so we gave the code away, so it's on GitHub. It's just we started the product, like so many open source projects that are started by companies. But the idea is like to grow this as a community and to build a community around it. So HP doesn't have any. The only thing HP does is if your business depends on distributed R, like we offer commercial support. Like Hadoop and all the other guys. But this is for free. You can get the code and do whatever you want with it. Okay, so I'm going to do a quick demo around those concepts. So for those of you who don't know, this is IPython. So they changed the branding, now they call it Jupyter, but it's still IPython. So IPython is like a fancy console. So this web page is connected to an R session in the backend. So we can run R commands on it. And the nice thing about this is like you can do your data analysis work and you can like track every step. Like you can see like all the steps you took like to come up to the final solution. And this supports text, but it also supports images, tables. So it's like a console on steroids. Okay, so. Okay, so here it's like an R console, so we can run R stuff. So this is like an R session. This is so you guys know it's real, like this is the time now. Okay. And the way to use distributed R, it's very simple. You just load the package with library distributed R. Okay, this is just shutting it down in case it's running when we set up this. And then, so the only configuration that distributed R has is that XML file. So they are basically, we are specifying like what is the master and how many workers we have. So in this case, we have one master and one worker. And in the worker, we say executors equals 0. That means we are going to run one worker per core. So this machine has 4 cores, so we are going to run 4 workers. And then once we have, by default, this is the XML you use, like a local setup. So to start distributed R, you just need to run distributed R start and optionally pass the configuration files. Okay, so this is starting. Okay, so now if we run distributed R status, yeah, there we can see like we have one worker. That worker has 4 cores and 7,900 something, which is the memory. So it's like 8 gigs of memory. I don't know what's. Okay, and the next step is just creating a D array, like the data structure we talked about. So creating the arrays is very easy. So the first argument is like the total dimensions. So how many rows and how many columns your data has. And the second argument is how you partition that data. So in this case, we are partitioning in 2 by 2 blocks. So in the end, we have 4 blocks. And then the next thing is, let's say we want to initialize the distributed array. So that's why we have the for each construct. So for each has 3 arguments. The first one is an index. So basically, this is looping over the partitions. In this case, we have 4. And it's looping in parallel. And for each of the workers, it's going to run the function that we defined there, which is the init function. Yeah. So in the init function, we just pass one of the blocks of data. Remember, like the D array has 4 blocks, so we pass one of those blocks. And in this case, we are passing an index, the index I. And what we are doing is we are just initializing that block of data. So we are creating a matrix that's 2 by 2, and the data in that matrix is the index. So if we run this, and we run the for each, okay. And on the last step, we are calling get partition. So what get partition is doing is like it's fetching that data that's on the workers. Remember, like we have 4 workers. Each of the worker has 1 block. So now we are fetching that data in the master, and we are printing it. So now you can see what we did. It's like each of these 2 by 2 blocks, we are initializing it with an index. So this is basically how it works. You have your distributed data structures. You split your data across the cluster, and then you have for each to run like these computations. Okay, let me go back to the slides. Okay, so that was like the basic concepts. Using those basic constructs, like we put together some common machine learning algorithms. So we have, for example, linear regression, which is used in risk analysis and trend analysis. So this is like for predicting a continuous output. Then we have machine learning classification algorithms, which is logistic regression, random forest, and k-means. So with k-means, you can split your data set in different clusters. And finally, we have PageRank, which is a graph algorithm. And the good thing about these algorithms is, like, compared to the normal versions in R, they are scalable and high performance. So for example, we can run regression on billions of rows in just a few minutes. Okay, and now I'm going to switch to Vishrut, which is one of the data scientists working on our team, and he's in charge of building like parallel algorithms using the platform. So he's going to go over that, and he's also going to like go through the March Madness use case. Sure.
So I'll go over a use case using the March Madness data to try and predict a good bracket using distributed R. So say we have the general problem is trying to predict good bracket for the March Madness, which is a basketball competition, if you guys don't know. So what we have for our starting data, for example, is a whole bunch of games played from 1985 to the current season of college teams. So what we can try and do is try and learn a good model for which features are good for basketball. So in our current data set, we have features such as blocks, steals, assists, all these various things in basketball, right? So what we can do with our data set is just run a simple model by trying to determine the important features and all these things for winning a game. Then once we've got a model of who wins a game, we can try and predict who will win a specific game between two teams. So the way we do that is we try and predict summary statistics for each team that we can plug into the model that we've trained in the previous step. So this is just a very simple model to try and predict who will win an individual game. And once we can do this, we can fill out for our bracket one step at a time. So the model that we can use to try and predict who wins a basketball game, we can choose, for example, a simple random forest model. So in random forest, what you try to do is build a whole bunch of decision trees. Decision trees are simple trees where at each node you try a very simple decision rule and either classify your data going to the left child or right child. So say you want to build 100 of these decision trees. If you were to do this in standard R, this might take quite a bit of time. So what you can do is, say you have more machines. In this case, let's say you have 4 machines and you want to build 100 trees. What you can do is tell each machine to build 25 trees and then return them to the master. And that is a very simple way that you can create a parallel algorithm from an existing sequential algorithm. And this is what we will do to predict the March Madness bracket. So this is our bracket. As you can see, it does okay. There's a lot more green than red. Green represents correct predictions. So, you wanna? So we're going to show you a quick demo of how we got this result.
Yeah, this is like. Can't see it.
So again, the first step is starting distributed R. We didn't provide the config file, so it's just running locally. So as always, the first step in these things is to load in the data, do some initial pre-processing, which is the first step here. So I'm not going to go into too much detail about that. The second step is calling the random forest model, which is over here. So as you can see, the format, or the function signature is actually very similar to the random forest function signature that is a very common R package. That is intentional. We want to try and have a very easy learning curve, or a very low learning curve. So we can pass in a model, or a formula to try and predict. So basically this formula we have here is signifying we want to try and predict who wins given features such as team one's field goal accuracy, rebounds, assists, blocks, so on. So, okay. So you can print out the model and you can see gets an accuracy of almost, error rate of almost 50%. So what that tells us is that we have an okay model of predicting who will win a game based on these statistics. So if you had been watching carefully in the formula, you notice that I don't give the individual team scores, so I don't give how many points each team scored. That would basically be cheating, right? So the next step is basically just predicting the individual game, which is this chunk of code. So what we're doing here is just reading in data on each individual team, computing average statistics on each team, and trying to predict who will win at each game. So basically, if we go back to the bracket here.
Sorry, you have like a complex setup with VMware. Okay.
So you go back to the bracket. What we do is we try and predict round by round who is going to win. So for example, we first predict who's going to win the game between Villanova and Lafayette in the top right corner, and then keep going down. And basically doing this repeatedly, we can create this bracket. And so that was a quick demo on how we can achieve a pretty complex task, such as predicting a March Madness bracket in a reasonably simple way using distributed R.
How does this rank on Kaggle?
Do you wanna take that one?
We didn't actually submit it. We just did it very quickly yesterday.
So, quick question, not directly pertaining to the position. So, clearly it would make more sense to use this year's behavior as opposed to...
Yeah, so what we did was we trained the model that predicts which team is going to win. So basically that model is just trying to learn what factors are important in basketball. So for example, are blocks more important than assists, all these things. So we can use past data for that, but once we want to try and compute summary statistics of teams, we only use this season's data.
In terms of feature, you're using teams, but typically the players in the team also matter.
Yeah, so we didn't have that data available. So we were restricted to team statistics.
You talked about efficiency as a key aspect of distributed R with R.
Right.
In your basic one, which aspects? That is a really different. Only the decision trees? In terms of undertaking, where else is it important?
Basically, if you have a large amount of data, the data in this case was 100,000 rows or something, corresponding to 100,000 games since 1985. So when you have such a large amount of data, you can imagine you might even have larger than that in production cases or something. So you might not be able to store all this data on one machine, so you might need to distribute the data. So if you have standard R, you can't really do that, right? You can't really do anything if your data is too big to fit in memory. You're going to either have to truncate it or use something else.
What data formats do you support any distributed data formats?
Maybe.
Yeah, so HDFS is coming up. If you are talking about data sources, like what we have now is we have a very good connector for stacking data from databases, more concretely HP Vertica. So we can load like 500 gigs in less than 10 minutes. If not, we can read data from the local hard disks. Like regarding formats, like we support whatever R supports, so we can read JSON, CSV, all of that. Sure.
So this distributed are always like breaking data into 4 blocks, or is it?
No, this depends on your cluster. This was just an example we have for workers. Usually you want to split your data evenly across your cluster. If you have more machines, more parallelism, you can split the data in more chunks.
That actually kind of extends on what I was going to ask. So if you have 4 separate computers that are all analyzing data that are then sending it back to the master, what confuses me is if you have an unequal sample size between those 4, how do you rectify that each of the 4 have different inferential statistics like standard error, the mean, standard deviation? You have potentially 4 separate analyses. What is the algorithm to then combine all that to one standard error mean?
Do you want to handle that?
So that is, I mean, there is some work in redesigning the algorithm. You do have to, you can't just get away with, building one model here, one model there, and then training or predicting using both of them, right? So there is some work in redesigning algorithms to use this parallel framework. Yeah.
Is that like all the distributed? Is there a distributed memory kind of image that each machine has? I mean, in terms of ability to be able to see what is going on. It's a read-only structure, I believe that, but because it's a distributed R. So, but is there a distributed memory kind of a thing that you need to use, or is it all local?
So it's not read-only, but so for example, you can create new partitions, right? So if you can create new D arrays, for example, and create new distributed structures. What was your other question?
Does each machine have are the machines able to share certain kind of distributed memory?
Yeah. So each machine works on its own copy, and then the master has the metadata where all the chunks are. So at some point, like your algorithm, you work in parallel, and when you need coordination, you go through the master. But usually, you don't need to move all the data back to the master. Either you move a smaller data, or the master just does coordination. So. Does that answer your question?
Yeah, but suppose we are trying to create a new data frame. What actually happens? I mean, in terms of how the four machines will coordinate in the new data frame.
So you would have to declare it on the master. So the master would then tell each of the workers do this operation to create this new data frame. So for example, if each of them have like a distributed file system to read from, the master would tell them go read from this file, worker 1, worker 2 read from this other file, something like that.
Yeah, I mean, so that is when you read files, In this case, the example I did, we initialize the data ourselves, right? So when we send the code to each worker, we say, hey, worker, initialize a 2x2 matrix with this data. So the master knows like which partition each worker has, but you send the code to the workers, and the workers create the data. Or read the data from a file system, or HDFS, or a database.
Okay, maybe we can do a last question and then finish the presentation and do the rest of the questions.
One of the earlier questions, you talked about redesigning the algorithms for, uneven distribution data between the four. So, is that one of the major challenges? What are the challenges that exist?
Yeah, so that is a major challenge, right? You can probably get a reasonable result doing some quick solutions. For example, this random forest, you can probably just do this in like 10-20 minutes once you're familiar with the system, right? But to create the real algorithms, you need to redesign a lot of the internals of R packages. So
it's like there are two levels of people, right? One is like engineers, they know distributed systems, they know machine learning. So those people create the algorithms. And then if you're a final user, you just need to call it. So you just need to learn the API and call it. If you want to implement a new algorithm yourself, then yeah, you need to understand how the system works.
For developers, what are the challenges? What are the main challenges? That's what we're interested in. Apart from redesigning algorithms, yes, what else?
Well, I guess like in a distributed system, and this is very algorithm dependent. So depending how you structure the computation and how much communication you have, so your performance is going to suffer, right?
Yeah, so for example, you want to avoid moving large amounts of data, otherwise that will be very slow. So it's basically a little bit different in designing the algorithms, but other than the algorithm design, I think the platform code is very much
To implement algorithms on this, you need to be like a distributed systems person. I mean, if you want to do a good job, you need to be a distributed systems person and a machine learning person. If you just want to use it and get the scalability and everything for free, you just need to, to learn the API, and any data scientist can use it.
Do the nodes have to be homogeneous?
No.
His question was, what are the problems you are facing when you are implementing this distributed algorithm? That's what.
Oh, okay.
Yeah.
So, I mean, it's kind of similar to designing a normal algorithm, right? But the only additional constraint is that it's now distributed, meaning your data is somewhere else. You have to minimize communication, I/O, and other than that, it's very similar to designing a normal algorithm, right? There's no like specific quirks of the platform that you have to really learn or anything like that. So let's move on.
So if you weren't a big fan of Jorge's IPython notebook, where he basically just showed you lines of R code and ran it all together, here's something a little bit more graphical, a little bit more interactive. So we built something using Shiny in R, which is basically, if you don't know what it is, it's a package in R that allows you to easily wrap up your objects, your functions, and your R code, and basically transform them into nice web pages with JavaScript and interactive elements and stuff like that. So we have this interactive demo available. If interested, you can run it yourself. We can give you the IP address. Basically, what we did here was hook up an instance of distributed R running in the background, and this web page will allow you to play around with this algorithm that we are going to demonstrate here. So in this particular case, we are running the random forest algorithm, and we are going to do it side by side, showing how much faster distributed R is compared to R. In this case, we're only using 3 cores for distributed R, so we only have a measly parallelism of 3. But if you have a larger cluster, you have larger machines, you can get even better parallelism. So let me talk a little about the data set. So for this, we're using some census data. And also, we're using the census data to predict income. So in the data, there are something like 40 features, a combination of job and income attributes and personal attributes. And we're going to use these features to predict whether the person described by these attributes makes more than 50K a year. Okay, so I'm going to hit this button, and it's going to launch both a distributed R instance and an R instance. So pay attention to the bars over there. At this point, distributed R is already done, and the R is not even halfway through the thing. So basically, what you can already see from the distributed R results, they're actually, the top and bottom graphs are exactly the same. They computed the same thing. But the results that we're showing here is basically ranking the importance of the attributes. And here we see that occupation, obviously, is clearly the most important predictor of income. And the second most important one is dividends from stock. Third is age, followed by capital gains, industry, education, yada, yada, yada.
So it looks like the 2.47 is the factor, but it's unclear, because if you are reading data locally, why is not closer to 3?
I mean, there are some, so we're actually using a pretty small data set. So what's included in the timing includes some of the overhead from starting distributed R, and also from sending the data around and setting everything up. But actually, if you increase the size of the data set, it will get closer to 3. So actually here we do have some plots here. We've done some experiments so that show that it is actually pretty scalable, at least amongst the algorithms that we've implemented and we provide. So k-means, random forest, linear regression, and the synthetic graph algorithm, they all have roughly a linear speed-up relationship. So as you increase the number of cores, the amount of time that it takes to complete your algorithm goes down linearly. So, if you're worried about it being difficult to use, if you have to actually write a lot of code, no, that's only true if you're designing your own algorithms for distributed R. If you're just a user and you're using one of our available algorithms, the differences are actually quite minimal, right? So in the vanilla R case, you would simply, to train a model, you would invoke the random forest function, right? Which is one line of code right here. In the distributed R version, it's really as simple as loading up the packages in R, distributed R, loading the HBD classifier package, which is our R package that contains our algorithms, invoking distributed R start, which starts up the system, and then simply calling the parallel version of the random forest. And because we design our algorithms to be roughly compatible in terms of models, it's going to give you something that's very similar to what you would have gotten just by writing kind of vanilla. Yes?
There seems to be an asymptote in your graphs of the performance increases.
I mean, yes. So I guess this is probably an artifact of the small data set size.
Yeah, this data set. So basically, we have the constraint like it needs to be small enough, so we click and it finishes in 10 seconds. But it's like the minimum size that gives an speed up. If you have bigger data sets, that asymptote happens way later. Like it scales pretty linearly. Like we've done tests with 500 gigs data sets, and it's pretty linear. This is just because this one is small. It's 10,000 rows.
What is the biggest data set you tried? Biggest data set?
It's like 500 gigs.
Yeah, between 500 and 1 terabyte.
500 terabytes?
No, not 500 terabytes. Between 500 gigs and 1 terabyte.
No. So based on your architectural vector is the kind of handling the case of the partition doesn't match to the algorithm. So you upload the data to the master. So there seems to be some scalability limit.
We don't move the data to the master.
Because then partition doesn't align well with the algorithm, meaning storage already. We store the data already. And if data partitioning in algorithms doesn't match with actual physical location of data, how do you solve
Yes, so the primary thing that we're working with are distributed objects, right? So these partitions of the distributed objects don't stay in one place. You're right, there's going to be some data movement, though we have some intelligent heuristics by the master whenever it receives a task. It looks at each task what the partitions are that are involved in that task, and then it tries to minimize data movement based on that. So whatever it will, each task is basically one that will be run on one worker. So it will look at all the data that is required for that particular task and move the data, if necessary, though trying to minimize it, to that worker and then execute it. So there is going to be some movement.
Between workers?
Yes, between workers. That is correct. Though, I mean, to minimize that is both the task of the platform, how intelligent the platform is, and also design of the algorithm is also important. Yes?
So, can you contrast it with RDube and the RMR package?
Which packages?
The RDube, with the RMR package?
Yeah. So this is like a generic comment with Hadoop and MapReduce. So in this framework, we are basically targeting machine learning algorithms which are iterative, right, in nature. So if you want to compare with something, this is more comparable to a Spark. So the problem with MapReduce is like every iteration you are going back to HDFS, right? Like every mapper like leaves the results on HDFS, and then you schedule the next task, right? So for machine learning, graph algorithms, and so on, these kind of systems work much better than Hadoop. But conceptually, it's similar. Yeah, some concepts like, like having like this distributed data, like shipping the code to the data, those are similar.
So have you tried to compare this to the Berkeley machine learning library?
Not to that one, because...
No, wait, I mean Spark based.
So we've done some comparisons with the Spark. Like we have a paper coming up in Sigmod. The performance is pretty similar, right, to a Spark. Weka, I don't have personal experience, so I think it's like a Java library, right? I cannot talk about that one. Do you mean like total time it takes to train those models, or? Okay.
So we didn't really measure the speed up, but the actual model took less than 1 minute, I think, to train with over 100,000 rows. So pretty good, I guess.
Yeah, I guess like
the data set is way bigger than the Shiny demo, right?
Yes.
So yeah, you can get like much more speed up, especially if you add cores and machine to the problem. So,
What is the underlying communication method?
So we use 0MQ to 0MQ. Are you asking by the underlying communication framework, like the messaging? Yeah, we use 0MQ. There is communication between the master and workers and between the workers, like both code and data. So we use 0MQ messages, and we use Google protocol buffers. So we encode the messages in Google protocol buffers and send them using 0MQ.
Do you partition the data based on the task queue you have, or the data is like statically partitioned?
So I would say that you partition the data depending what cluster you have. So, yeah, maybe you can add something else.
So I think you're asking who is responsible for partitioning the data? So usually the user will partition the data because they have to load the data somehow. Assuming they want to load the data in a distributed way, right? They will be responsible for partitioning it. But if you just send the data through the master, while it would be inefficient, the master will distribute the data equally for you. So, does that answer your question?
Well, I mean, like, if the data is already partitioned and you would apply the algorithm, sometimes, the algorithm would go and would need some partition of the data and would keep a communication with one party, and this would not improve the performance. Or I mean, like, there should be some way to distribute the data in a way that, you keep all the processing in parallel. Otherwise, you would not benefit from it.
Yeah, so that is very algorithm specific. The person who's designing the algorithm would either try and repartition the data or ask the user to partition it in some specific way. But it's very algorithm dependent.
This is a strictly in-memory compute, or is memory and physical?
It's in memory.
Once it's distributed, everything is in memory.
Right.
What if the data frame is bigger than your RAM?
Yeah, so one of the things we're going to be working on is spilling to disk.
You need to buy more servers, man.
So in that case, the performance will slow down.
Right.
Okay. Okay, so hopefully by now, you got some interest in distributed R. I think, especially for data scientists and people that use R, especially if you are working with big data, this can be a very interesting tool. You can run regression on billions of rows in minutes, graph algorithms in 10 billion edges. You can load data very fast from the databases, and the best of all is it's open source, so you can play with it. So let's say you're interested, you wanna do something with it. What can you do? So you can collaborate with us. The code is up on GitHub on this URL. You can just try it, play with it. If there is an issue, you can report it. If there is an algorithm that's not there and you like to use, and after what you saw, you think you can implement your own algorithms on the platform, we'll be very happy to integrate your changes. You can send us a pull request and we'll integrate the code. If you're just interested in using the software, you can go to that URL and download binaries and read the docs and just use the software. If you plan to use this software for some production critical stuff, so we also provide commercial support. Okay. And to finish the presentation, I'd like to finish with this quote, which is by William Gibson, which is a science fiction writer. So it says, "The future has already arrived. It's just not evenly distributed yet." Maybe some of you have heard this from Jack Dorsey, the founder of Square and Twitter. So I think it captures pretty well what we as people that do new products and have ideas do. And it's basically in our work, in ourselves, the future is there, right? We are already thinking in things about the future. So our only job is to distribute and sell those things to everybody and to the world. So that's it. Thanks a lot for having us here. And if anybody has more questions, we'll be happy to answer.
Now or after? Will you take now? Okay. So typically, does each node act independently? Can you use all the CRAN packages?
Yeah, you can use CRAN packages. So this is regular R. So in your code, you can import other packages.
And so the distributed component is essentially related to memory management.
Yeah, basically the distributed component is just splitting the data across the workers, and then each worker is running R. So you can like use any package there.
So are you asking if you could just use the R package and just plug in your distributed?
Yeah. Suppose I want to use dplyr or something. I have any CRAN package. Is it? Can you use it?
Right. Yeah. So you can't quite do that. You would have to make some changes probably.